Hello, my name is Yeonjoon. I'm currently an assistant professor at Hanyang University in South Korea. My talk today will be about using Sonar for liveness detection to protect smart speakers against remote attackers. This work was done in collaboration with Hanyang University, Indiana University, Chinese Academy of Sciences, and University of Virginia. Smart speakers such as Amazon Echo and Google Home are popular. According to VoiceBot.ai, as of April 2020, 87.7 million adults own a smart speaker. Also, Amazon stated that there are now more than 100,000 Alexa skills worldwide. Besides the basic functionalities, smart speakers also provide critical functionalities. Good examples are access banking services, send money, open front door. However, once smart speakers are attacked, such critical functionalities can cause serious consequences. Let's see what can go wrong. As many of you already know, smart speakers take voice commands from the users and perform various activities. The problem is the fact that smart speakers also respond to voice commands coming from other speakers. In our homes, there are various types of network-connected devices with speakers. However, according to recent reports, many vulnerabilities are found from such devices. By exploiting the vulnerabilities in the network-connected devices, remote attackers can hack into the devices and send malicious voice commands. Furthermore, recent studies show that the voice interfaces of smart speakers can be cheated with crafted voice commands. To tackle such problems, we proposed Speaker Sonar, a sonar-based liveness detection system which aims to protect voice interfaces of smart speakers. We carefully designed the Speaker Sonar to meet the following goals. Provide non-intrusive user experience. Conduct real-time defense, which does not require additional training time. Use hardware similar to the current smart home devices such as the Amazon Echo. The key idea is to do a simple consistency check. We check whether the direction of the voice command is consistent to the user. Simply put, we want to make sure that the voice command is indeed coming from the user. To detect the direction of the user, we build a sonar system. Our system emits an inaudible ultrasonic sound. Our system then tracks the user's direction by analyzing the Doppler shift in the reflected signal. It's basically a sonar made with cheap hardware. But because we made it with cheap hardware, our approach can only track users up to 2 meters. As mentioned, the user can send voice commands. However, remote attackers can hack into network-attached devices and send voice commands as well. But now, since we have the user's direction, we can compare it with the direction of the voice command and pass when the direction is consistent with the movement. When the directions are inconsistent, we can simply reject the command. With our protection in place, the attack only works when the user, the hacked speaker, and the smart speaker is in a straight line. In other words, it means that the attacker needs to know the location of the hacked speaker, the location of the smart speaker, the location of the user in real time. Without such information, the attack becomes very opportunistic. The system I just showed is built with inexpensive devices. As you can see from how it looks, the Speaker Sonar basically imitates popular smart speakers, such as the Amazon Echo. This is the overview of the Speaker Sonar. Please check our paper for the details. These are the frequency spectrum examples analyzed in our system. The blue box shows the spectrum of the transmit signal. We designed this wideband inaudible signal to build a sonar with cheap devices. We used a wideband signal because wideband signals work better in reverberant environments such as our homes. Before we actually can get the direction of the user, we process the received signal through several steps which eventually ends up with the signal in the red box. We basically removed all the unnecessary information and only left the Doppler spectrum to get the user's direction accurately. Please check our paper for more details. The following is a room that we evaluated our system. As shown in the table, our system successfully passes legitimate commands and rejects malicious voice commands. We also place the hacked speaker in different angles from the user and evaluate our system. As you can see, our system successfully rejects malicious commands that are sent from 20 degrees or more from the user. We further evaluated the accuracy of common behaviors. As you can see, while larger movements get well detected, precision decreases when movements are small, from 2 meters or more, perpendicular from the speaker. This is because the Doppler shift gets weaker in such cases. Hope you enjoyed our work. Please check our paper for more technical details, micro-benchmark evaluation results, interesting online survey results, and discussion. Thank you for your time, and feel free to contact me if you have any questions.